So in previous sessions, we've looked at the properties of our Milky Way galaxy. We know it's a spiral galaxy. We've talked about the bulge, the disk, and the halo as the different structural parts of our galaxy. But ours is one of many billions and billions of galaxies. So we probably don't want to base our entire understanding of galaxies based on a sample size of one. So what we're going to be doing in this session is looking at other galaxies, comparing their properties and identifying, are there certain classes of galaxies? Are there different types of galaxies? And what are some of the general properties that those galaxies have? So we're going to start with the spiral galaxies. Again, our Milky Way galaxy is a spiral galaxy, so it's probably a little bit egotistical to start with that one, but we'll go with this one. And these spiral galaxies today are the most common type of massive galaxy. So most common type of massive galaxy today. We are going to see how there are other more common types of galaxies just as a whole, but if it is a relatively high mass galaxy, it's probably more likely to be a spiral galaxy than any other type. We'll talk about, many more types of smaller galaxies in a little bit. So let's talk about some of their general properties. We've got a couple of examples of images of some of these spiral galaxies. In our own local group of galaxies, which contains a few dozen galaxies, the three largest ones, the Milky Way galaxy, Andromeda, and Triangulum, all three of those are these spiral galaxies. So even though there's more of the smaller types of galaxies, if it's a massive galaxy, it's probably going to be a spiral galaxy. In terms of its structure, we have the bulge, the disk, and the halo. So bulge, disk, and halo. So again, this is fairly easily identified in images. If you see some of these spiraling disks, that's going to be the most direct way of identifying that we're working with a spiral galaxy. What do these contain? Well, we're going to see some ideas of signs of star formation. So I just want to quickly reiterate what we've talked about earlier about signs of star formation. Whenever you see these blue speckles, let me zoom in on this image just a little bit so we can see this a bit better. Whenever you see some of these blue speckles, those are going to be the young type O and type B main sequence stars, the ones that are very high mass, very energetic, very luminous, so very easy to see compared to other types of stars, but they only live for a short time. So if you have these O and B main sequence stars, if those are still there, it's probably the fact that they formed relatively recently, since they only last, maybe a few tens of millions of years for type B stars. Type O stars even shorter than that. We also have these pink patches, these pink splotches, which are signs of ionization nebulas. So we talked about the blue speckles and being a sign for star formation. Those O and B stars don't last very long, so they must have just recently formed. These pink splotches, those are the ionization nebulas, where I have a cloud of predominantly hydrogen gas. Still, the proportions are still 3/4 hydrogen, 1/4 helium, 2% heavier stuff. But we have this cloud of hydrogen gas, and if I have some of these relatively nearby O and B main sequence stars, they are very energetic and give off a lot of ultraviolet light. That ultraviolet light excites that cloud of hydrogen gas, and it causes it to glow with that characteristic pink color. So these pink splotches, those are ionization nebulas excited by those O and B stars. And if you see either of these effects showing up, you've probably got some really good signs of star formation. So what do these things contain? Well, we have gas and dust. We've got these signs of star formation. Again, those blue speckles and those pink splotches. And if there's signs of star formation going on, then we're going to have both old and young stars. So both young and old stars in the disk. Again, this composition, it's pretty much in the disk where we find these gas and dust clouds, these signs of star formation, old and young stars. In the halos around these, you're going to find more of those older globular clusters, pretty similar to what we talked about for the structure of the Milky Way galaxy. Star formation, yes, in disk. So again, all these things are showing that these galaxies are going through that star-gas-star cycle. We said for the star-gas-star cycle, in the disk of one of these spiral galaxies, when stars go supernova, the gases that are in that galaxy, in the disk of that galaxy, slow down those ejected materials so they can be recaptured and recycled into these new generations of stars. When we look at the spectrum of these spiral galaxies, well, we have some little bit of light, big spike up in the spectrum. Not much light, not much light, not much light. Oh, another big spike up in the spectrum. So pause it for a minute and think, what kind of a spectrum are we looking at here? Is it a continuous spectrum, an emission spectrum, or an absorption spectrum? Pause the video for a second and try to answer that one. Yeah, so if we have these upward spikes, those are emission lines where lots of light is being given off at these particular wavelengths. And you'll notice that in this image, in this spectrum, it's those hydrogen alpha lines that are really strongly going through those signs of those emission lines. So the spectrum is an emission spectrum. And those emission lines are from these ionization nebulas, from these pink splotches. So it's the hydrogen lines. Hydrogen emission lines from the ionization nebulas. And again, that is a direct sign of star formation. If we see these galaxies giving off these strong emission lines, those strong hydrogen emission lines, that's going to be due to those gases that are heated by those O and B main sequence stars, those very energetic stars, and those are going to show up in the spectra of these galaxies. We also do get a few absorption lines owing to the older stars that are there as well, but the strongest features are those emission lines for spiral galaxies. Again, looking in more detail at the signs of these star formations, these are all examples of spiral galaxies. In this one, this is a visible light image. This one is looking specifically at those hydrogen emission lines. Again, inside of those spiral arms, we see those ionization nebulas shine very strongly, and those are the regions of star formation. In these other kinds of images, we get these blue speckles. Let me actually zoom in on this a little bit more. In these images, we get these blue speckles as well, showing that there are very young O and B main sequence stars. In these images over here, we have the Andromeda Galaxy. This one is in the visible spectrum. This one is specifically looking at that galaxy in ultraviolet light. Again, those O and B main sequence stars, those high mass main sequence stars that are very energetic but only live for a short time, they are going to be giving off a lot of ultraviolet light. So if we look at these galaxies in that part of the spectrum, those newly formed stars and those regions of star formation are going to shine very, very brightly. We can also look at the gas and the dust in these galaxies. So I'm going to zoom in on this as well, since we've already kind of talked about this. Inside of the disk, we notice that there are these darker regions. And again, I really want to highlight here, These darker regions are clouds of gas and dust. They are not dark matter. We talked about dark matter very briefly in one of the earlier sections, but dark matter doesn't even block light. So if there was a cloud of dark matter in front of, some source of light behind it, that light would be able to go through the dark matter without affecting it in any way. So these darker areas, that's not dark matter, it's these clouds of gas and dust. Okay. This is another image of a spiral galaxy. This is one of my favorite images of spiral galaxies. This one is looking at that galaxy, that spiral galaxy, but just edge on. Sorry, I should go this way. Just edge on, so we can see all of that gas and dust that's blocking out some of the light from the stars that are deeper in that the disk of that galaxy. This is another galaxy looking at that galaxy both in the visible part of the spectrum and in the infrared part of the spectrum. These clouds of dust and gas, if they start getting a little bit heated up to kind of like moderately low temperatures, that might be giving off a lot of infrared light. So if we want to study the gas and dust in these galaxies, looking in the infrared part of the spectrum is a useful tool to use. Now, there are further subtypes of galaxies. We're not going to worry about this very much. We have these barred spiral galaxies where it's got the disk, it's got the bulge in the middle and the halo around it, but it has this strong bar feature showing up and extending through the nucleus. We also have these lenticular spiral galaxies. They still have the disk, the bulge, and the halo, but they don't really have spiral arms like the other galaxies that we've seen have. Again, just pointing out that there are subtypes of galaxies. We're not going to worry about these specific subtypes of spiral galaxies too much, just knowing that there are further details and further patterns that we see in different groups of galaxies. So that's kind of the summary of spiral galaxies. They're the most common type of massive galaxy today. They have the bulge, the disk, and the halo. They contain gas and dust in their disk, signs of star formation, old and young stars, and they have emission spectra. So let's now look at another type of galaxy that we call elliptical galaxies. So let's switch over to these elliptical galaxies. In terms of their structure, well, they have a bulge in the middle, they have a halo around the outside, but they don't have a disk. So their structure is a bulge and a halo, but no disk. So when we talked about the star-gas star cycle, again, we said that if I have the disk of a galaxy that has lots of dust and gas in it, then if some stars go supernova, when it ejects those materials from the outer layers of those massive stars, when it goes supernova and ejects those outer layers, the dust and gas inside of that disk is going to slow down those gases, and the combined gravitational attraction of everything in the disk is going to cause that ejected material to eventually be recaptured and rain back down so it can recycle into new generations of stars. These elliptical galaxies don't have that disk. They don't have that method of recapturing material that was ejected in these supernova events. So it can't really form new generations of stars. So if there's no new generations of stars, we get none of those signs of star formation, no O and B main sequence stars, no ionization nebulas. So in this, we don't get any signs of star formation. So no signs of star formation. And these have little to no gas. Well, again, that means there's not going to be any new star formation, but we are going to have lots of older types of stars. So older stars. Mostly type K and M. These type K and M stars, think for a second, when we talked about those type K and M main sequence stars, what were some of their properties? So pause it for a moment and see if you can think of some of the properties of those K and M main sequence stars. Things like what their temperatures are, what their colors would be, what spectral features they would show, things like that. Okay, so these type K and M main sequence stars, those are the lower mass main sequence stars. They are lower temperatures. So instead of being that, white to blue color, they're going to be more red, orange, and yellow colors. And that's what we see in these images. The overall color is this kind of reddish yellow. So I'm going to add that into the structure. They're reddish yellow in color. They're this reddish yellow in color, and just kind of like a, either a relatively spherical shape, maybe a little bit of a football shape to that. So that's how the first way that you can identify them in these images is just saying, well, are they this kind of reddish yellow color in these different images? Well, if there's little to no gas, no signs of star formation, then what kind of a spectrum are they going to have? Well, this is one of the spectra of an elliptical galaxy, and their spectrums are overall going to be those absorption spectra. And what are some of the key features? Well, I can see some pretty strong sodium and magnesium line, so downward spikes there. I'm getting a couple of these wider gaps, some of those molecular absorption bands. And these are all the absorption features of older stars. So it's the same features that you get for lower temperature stars. Same features as type K and M stars. Those generally lower temperatures. So again, the spectrum overall looks like it's close to a thermal spectrum. Again, this is multiple stars, all their light combined together. But it's generally got that shape of a lower temperature star with those absorption features also associated with lower temperature stars. There's very few emission lines, as there's essentially no gas. You're not going to get those emission lines unless you have one of those excited gases, but we don't see that. Now, for the elliptical galaxies, we are going to be talking a little bit about these subtypes. And we're going to start with the dwarf ellipticals. These are the most common type of galaxy today. So most common type today. Earlier, we said, well, if I have a spiral galaxy, spiral galaxies are the most common type of massive galaxy today. But these dwarf ellipticals, which as their slightly non-PC name suggests, are on the smaller side. These are fairly small galaxies and mostly orbiting around larger galaxies. So they're smaller and orbit larger galaxies. So, for example, in our local group, I mentioned that our local group contains a few dozen galaxies. The three largest ones, the Andromeda Galaxy, the Milky Way Galaxy, and the Triangulum Galaxy, those three largest are all spiral galaxies. And around each of those, we've got a couple dozen elliptical galaxies, these dwarf elliptical galaxies orbiting around the Milky Way, orbiting around Andromeda, orbiting around in between these galaxies. So again, these dwarf elliptical galaxies, they're smaller, but they're much more common than some of the larger galaxies. We also have giant elliptical galaxies. And these are the most massive type of galaxy. So the most massive. These galaxies are very often found at the centers of clusters of galaxies. In one of the next sessions, we'll talk about a little bit more about large-scale structure and how galaxies tend to clump together, tend to form in groups and clusters, kind of like how stars form in groups and clusters. But these galaxies, these giant elliptical galaxies, are very often found at the very centers of large galaxy clusters and could be the result of many galaxies colliding with each other, using up all of that available gas in those collisions and the bursts of star formation that occur in those collisions. And then at the end of all of those mergers of galaxies, we're left with this one giant elliptical galaxy with still many other galaxies orbiting around it. So these giant ellipticals are often at the centers of galaxy clusters. So this is an image of the galaxy M87, which is a giant elliptical galaxy about 60 million light years away. And this is the center of the Virgo supercluster of galaxies. Our own Milky Way galaxy in our own local group is just at the very kind of outer edge of this larger supercluster of galaxies. So again, we're looking at this in visible light, in radio waves. There's some other stuff going on. We'll talk about what's causing this jet of material when we talk about active galactic nuclei in a couple of sessions. Now, there is this classification scheme, this Hubble's classification scheme. We're not going to worry about this one too much. Later on, we'll talk in more detail about some of Hubble's other discoveries that we're going to go into much more detail on. But there are these kind of classification schemes to talk about elliptical galaxies, ordinary spiral galaxies, barred spiral galaxies. But again, we're not going to spend too much time talking about this particular classification scheme. Okay, so we've got spiral galaxies, we've got elliptical galaxies, and the last one that we're going to talk about are irregular galaxies. This is the most common type of galaxy in the past. And I should kind of put a caveat to this one. So let me just say, so most common type in the past. And I'm going to put a little asterisk right there because with some new data that has been coming in from the James Webb Space Telescope, it seems that some of the spiral galaxies that we're going to talk about, when we talk about galaxy formation, it seems that spiral galaxies, even from some of the initial data from the James Webb Space Telescope, those seem to have formed earlier on in the history of the universe than we thought. So there are still a lot of open questions about galaxy formation. We'll talk about it briefly in one of the next sessions. But at least for now, we still think that these irregular galaxies were quite common in the past. So let's talk about some of them. These are some examples of irregular galaxies that we can see around us today. Structure, not really any. So not much structure. We just kind of get this, weird assortment of stars and gas and dust clouds. I kind of think of them as if you've ever tried to fry an egg and the yolk of the egg breaks and kind of spills out in a weird random direction. It kind of reminds me of that. I don't know if anyone else sees that in some of these images. But we'll go from there. So it doesn't really have a central bulge. It doesn't really have any halo to it. It's just kind of this weird smearing of stars. But if we look at these images, Do we see any of those signs of star formation? So again, our signs of star formation are the blue speckles for young O and B type stars and pink splotches for those ionization nebulas. Pause the video, take a look at those images, and see whether you think that there is star formation going on in these galaxies. Well, if we look at these galaxies, blue speckles, yep, I see quite a few blue speckles in here. Pink splotches, yep, I see quite a few of those in these images. So we do see those signs of star formation. So signs of star formation, yeah. And that means that these irregular galaxies, they have to contain gas and dust. Because if it doesn't contain gas, well, what is it making those new stars out of? Since there's star formation, we're going to have both young and old stars. So young and old stars. But again, it's not really in that much of an ordered setup. We just have kind of this weird, distribution. Again, talking about the most common type in the past. Well, it's important to remember, and we're going to go into this in more detail again. We've talked about it briefly in previous sessions. But when we're looking at distant objects, the further away that object is, the longer it has taken that light to reach us. So the further away that object is, we are looking further and further into the past when we're looking at objects that are further and further away from us. So when we use telescopes to look at very, very distant objects, we are literally seeing them as they were in the past. And again, there's new data coming in from the James Webb Space Telescope, but when we have typically looked at further and further distances, well, we see more and more of these irregular kinds of galaxies, more and more of this kind of lack of structure of galaxies. Some of these might be galaxies that are still currently forming, again, with a big asterisk here, because the James Webb Space Telescope is able to look at parts of the electromagnetic spectrum that will actually give us a much better look at how those galaxies were acting in their earliest stages of formation. So a lot of this information might become modified or might become obsolete as we gain new data. Remember, in any kind of science, all of our conclusions are tentative and subject to revision given new data. But again, the main idea that I wanted to just mention here is that the further away the object is, the further we are looking back in time, because it takes light a finite amount of time to actually reach us from those objects. So we've got a couple of example images of this. These are the large and small Magellanic Clouds, are irregular galaxies that are orbiting the Milky Way galaxy. Unfortunately, these are only visible from the southern hemisphere, but you can actually see them with the unaided eye from the southern hemisphere. This is the small Magellanic Cloud in the visible spectrum. Notice we're seeing some of those pink splotches. And if we look at the same thing in the ultraviolet part of the spectrum, now we see some of those, more of those blue speckles, those very high energy O and B main sequence stars that are giving off a lot of that UV light. What about the spectras of these irregular galaxies? Okay. In terms of their spectras, how are they going to compare? Well, pause the video for a second and try to think through which spectrum does this sound more like based on what we've talked about with these irregular galaxies. The emission spectrum that we had for those spiral galaxies, or the absorption spectras that we had from those elliptical galaxies. Pause the video for a second and think, which kind of spectrum do we think these irregular galaxies are going to be giving off? Okay. Well, if these are showing lots of those signs of star formation, and including those ionization nebulas, well, that's probably going to be another emission spectrum. So we still have these emission spectrum, mostly from those ionization nebulas. Again, it's usually going to be the hydrogen lines that are being excited a lot. There are some other lines that also get excited. Again, because we have some of those young stars energizing some of those nearby clouds of dust and gas. Again, these irregular galaxies might be undergoing interactions with other galaxies, or further in the past might have still been in the process of star formation. In a little bit, we're going to talk about interacting galaxies. But again, there's still a lot of open questions about how these galaxies form. When did they exactly form? What were some of the mechanisms that were important during the formation of these galaxies? So we'll talk about those in more detail in just a little bit. This is an image. Let me zoom in on this once again. This is the Hubble Deep Field South, one of the longest exposures of the Hubble camera. And again, the James Webb Space Telescope, as we start collecting more data and going through the analysis and looking at the spectras from that, we're going to get more and more detailed information about what these galaxies were like further and further away, or further and further into the past. And in this image, we see some of these cases of spiral galaxies. We see a couple of irregular galaxies. Again, the largest ones might be those giant, these giant elliptical galaxies, that yellowish color, that yellowish kind of football shape. We see some weird irregular galaxies in here, galaxies that might be undergoing interactions. So we see this whole population of these different kinds of galaxies in just this one image. And again, these deep field images generally take just a tiny, tiny section of the sky, basically smaller than your fingernail, the fingernail with your pinky finger held at arm's length. It's a tiny little section of the sky, and just stares at it to try to see more and more of these distant objects. Again, all these little specks that you see on here, those are all individual galaxies in this image. And again, with new technology and the new James Webb Space Telescope, along with other kinds of observatories, we are getting more and more information about what these galaxies were like in further back in our universe's history. So I want to spend the last part of this. I'm going to zoom in on this one more time. And I want to just kind of run through a compare and contrast between these different kinds of galaxies. The numbers that are in here, I do not expect anyone to memorize these numbers. What I want students to be able to do is to compare and contrast between these spiral galaxies, the elliptical galaxies, and the irregular galaxies. So let's talk about some of these general properties. In terms of the masses of these galaxies, notice that the spiral galaxies, the lowest mass spiral galaxies, are significantly more massive than either the elliptical galaxies or the irregular galaxies. Again, today, if it's a massive galaxy, it's most likely to be a spiral galaxy. So in general, spirals are massive galaxies. Notice for the elliptical galaxies, we have some of these very low mass, or quite low mass elliptical galaxies. Those are the dwarf ellipticals. Those are the most common type today. But we also have these giant elliptical galaxies, where they are most likely the result of the merger of many smaller galaxies. So these giant elliptical galaxies, they do kind of max out the scale on the largest galaxies that we see. For irregular galaxies, well, they're kind of middle range. They're not the highest mass, they're not the lowest mass, they're kind of in this middle range. In terms of the sizes, the diameters of these galaxies, same kind of thing. Our Milky Way galaxy is a moderately large one, but the radius of our Milky Way galaxy is about 100,000 light years. This goes from 15,000 to 150,000 light years. Our Milky Way galaxy is kind of a, slightly above average mass spiral galaxy. But even the smallest spiral galaxies are relatively large compared to the smallest of the ellipticals and irregulars. Elliptical galaxies, again, those giant elliptical galaxies are also the largest of the galaxies that we see. They are the highest mass galaxy, but they're still pretty rare. Irregular galaxies are on the slightly smaller end of this scale. Not ridiculously so, but a little bit smaller. In terms of populations of stars, all these different types of galaxies have old stars. All these different types of galaxies that we've talked about, they started their formation probably around 12 to 13 billion years ago. And our universe itself is about 13.8 billion years old. So all of these started out pretty early in the universe's history. A few hundreds of millions to maybe around 1 billion years after the Big Bang, these galaxies were already starting to form. So all of these are going to contain those older stars. And those stars that last the longest are those K and M main sequence stars. So whatever else the galaxy has, it's going to have those older K and M main sequence stars. However, the galaxies that still have dust, that still have gas and dust clouds, those are the ones that can form new stars. The spiral galaxies have that way of recapturing gases that are ejected during those the ends of stars' life, during those supernova events. Irregular galaxies still have a lot of gas there, so they can form new generations of stars. So only those galaxies that have gas have those young stars. That's an important connection to make. If it has gas, it's probably going to have young stars as well, because there's something to make those stars out of. If there isn't any gas, well, what are you going to even make that new star out of if there aren't any of these giant molecular clouds to start with? So if there's no gas, there's not going to be any new stars, all old. But if there is gas, you're going to get both old and young stars. Again, for this diagram, I do not expect anyone to memorize any of these numbers. All I want is to be able to compare and contrast between these different types of galaxies. And in some of the next sessions, we'll talk about more of the more properties of these galaxies, active galactic nuclei, how we measure the distances to some of these galaxies, interacting galaxies. We'll be talking about all those concepts in one of the next videos.